everyone, and welcome to tonight's live stream where we're hopefully going to save you from absolutely crashing your computer science GCSE. I'm only joking. Hopefully the revision you've done will smash it anyway, but let's see where we go. Now, not a great amount of time for us tonight to just have a chat, so I'm going to go straight into it, but I do want to start with telling you a little bit about what we know so far about the exams. You've sat some, you know there's a wild mixed bag of what's happening. In computer science, we've had exactly one exam so far, the AS exam. And whilst they said the same things that they've said to you, that there'd be no surprises, they have reworded about a third of the questions on the paper. That does mean that it might seem a little tough, but you just need to take your time, really read those questions and see what they're asking about. I mean, the positive thing we've got is we've got a list of exact topics that we need to look at. And I'll just jump over and we'll have a look at that. Pop myself up here. So on the screen is just a simple print screen of what the WJEC have said will be in your exam tomorrow. We've had this since January. You've seen it before, and certainly it is something that you are aware of. Certainly my class, I've popped this on the Google Classroom for you as accommodations 2022, and it's been there for a while. Although they say that you should teach it all, and of course we have gone through everything, this is apparently what they will assess on their exam. Now, a few people are saying stuff like basically everything. It's not. Honestly, this is a massive reduction in the amount of content. There's not quite as much there, and a lot of it is the classics. We'll go through all of this tonight within the hour, just as a quick refresher, but do go and practice your stuff. Each of these sections is smaller than it would be if we were teaching it all. And of course, some of them, there's barely anything to teach in them anyway. So let's go through, let's have a look. I suppose before we start, I just need to be 100% clear with you. They could ask questions that are not in this list. They could ask questions from anything. Hopefully they won't. But if they do, it's worth having a quick read through everything, a quick flick through, so you're at least aware of it. But this is the stuff that they say you should concentrate on. So let's get started with our first section, hardware. I'm going to work through all of these tonight in that order that we've just seen them, finishing up on environmental issues. Okay, so what you see in front of you is the CPU, the main part of the computer, the bit that does all the processing. The CPU is the big purple square, and we've got three different parts to it that you need to know about. The shapes might be important, so it's well worth remembering the shapes. The upside down trousers are the ALU, the arithmetic and logic unit. This bit does all of the maths and all of the logic comparisons. So whenever we've done an if statement, that is the component that is worked out. We've also got the control unit in the circle there. That is the bit that controls the speed of the computer, and particularly the clock speed. So this is the bit that's going next instruction, next instruction, next instruction. It's keeping the speed of the computer going by maintaining the clock speed. Now, if we want to overclock our processor, that's what we need to change to increase the rate at which it tells the computer to do the next instruction. Our registers as well are small bits of memory. They are the smallest bit of memory in the computer. They are the size of a word space, and a word space is the amount of bits that your computer runs at, so 32 or 64. And there's lots of them. There's some specialty ones like the ALU, the CIR, stuff like that that you would have looked at. But as long as you remember the registers are the memory, you'll be in a good place. Now, aside from that, I'll just bring this one up. We can have the slides. I'll pop the slides in Google Classroom after this. I'm going straight into an A-level live stream after yours, so it might be a little bit later, but I'll get them to you as soon as I can. So aside from just the parts, we've also got the buses. Now, the buses are just, you can imagine them as little cables. They're not actually cables. They're what we call traces, which are directly on the silicon, but they are cables in essence that can carry the data around the computer. You've got your data bus, which carries the data. You've got the address bus, which carries the address. And you've got the control bus, which carries the control signal. All those send that information around the computer. So aside from that, all of these instructions I'm talking about are part of von Neumann architecture. You know John von Neumann is my favorite mathematician, but he invented this style of architecture where the instructions, which are these things on the left here, and the data, this stuff on the right, looks the same. They're in the same format. They're going to be going through and seeing all that. The address on the right-hand side is literally the location in memory. And as far as we're concerned, it is one of these lines here in machine code. Von Neumann architecture is based around 3 parts: the fetch, decode, and execute cycle. Fetch means we get the next instruction from memory, so we pick up the next one of these. Decode means we pull in that entire line and we work out what we should be doing. And execute means we're actually going to do it. Now, this machine code is made of 2 parts. The instruction, or the technical term is the opcode, is the left-hand side, and the operand, or the memory location, is the right-hand side. So the first one could be anything really. It could be like add this memory location into the accumulator. And pick up on Ben's hilarious joke here, because yes, Ben, he is, as you well know, he is a singer, and he's one of my favorites as well. Different Newman though, Gary Newman, not John Von. Anyway, hardware, von Neumann architecture. That's what's running on the processor. These individual instructions are what are stored in the registers. These are what are being processed by the ALU when we do the execute part of the code. And the control signal is the bit that goes next, next, next on the fetch, decode, and execute cycle. Clock speed then is controlled by the control unit, and it's the number of those fetch, decodes, and executes that can be done per second. That's measured in hertz, or instructions per second. We are in the gigahertz region. Most CPUs are around about 3 gigahertz that you buy on a desktop nowadays, round about. That means 3 billion fetch, decode, execute cycles per second. The faster the clock speed, the more of those cycles it will do, and the faster the computer will run, but it will use more heat and use more battery power. So it's important that you keep that in mind if they ask you to compare those things. Storage is also important because a CPU can have cache memory. The registers, the fastest part of memory on the computer, is only really very small. We're talking maybe in the region of megabytes or kilobytes here, so not a lot of space really. The cache is a place where we can copy the most frequently used instructions and keep them close to the register. If we've got a big cache, we'll be able to store more of those more recently used instructions and pull them into the register a bit faster. If we have a small cache, there will be fewer of those more often used instructions available to the register, and it won't be able to find them as often. That's called a cache miss. And if there's a cache miss, we have to go out to the next level of memory to get the instructions. A CPU can also have multiple cores. If a CPU's got 1 core, like on the left, it can do one thing at a time. Literally, one of those fetch, decode, execute cycles, one at a time. If we got 4 cores, we can do 4 at the same time. And therefore, if we can break the job down into 4 parts, and we can do all 4 parts at the same time, and all 4 parts are about the same size, we can theoretically do it in a quarter of the time. And this isn't always true, because not every job is parallelizable, which is the key word you need to keep in your mind when you see that. Back to our CPU then. Well, our CPU is connected to our RAM. RAM is our random access memory. It is volatile. When the power goes off, the data goes off it, but there's plenty of it. There's a couple of gigs of this. So we can store all the instructions that the computer currently needs. Everything the computer is currently doing at the moment is stored in that RAM. Quick question. What jobs aren't parallelizable? Parallelizable. Non-parallelizable jobs are jobs where you rely on what you've just worked out to work out the next thing. This is things like working out prime numbers, even doing calculations that require the previous value to work out the next one. Anything like that is not parallelizable because we have to wait for the previous thing to be done before we can do this. So they're the sort of things we're talking about. Luckily for us, though, things that are parallelizable are things like graphics, audio, video, all the things we actually like using our computers and our phones for are parallelizable. So all the things your computer is currently doing is stored on the RAM, and everything else, long-term storage, is stored on like a hard drive. Now, keep in mind this. Your RAM is your primary storage. That is where everything that your computer is currently doing needs to be primary. If we need to get anything else, like we need to load Photoshop, we need to take it from the secondary storage, which is the hard drive or the SSD. That is non-volatile, and if we save stuff to that, it will be saved forever. But the difference is the speed. This is really slow compared to the RAM, and the RAM's really slow compared to the registers. Our cache then exists between those two. So the cache is keeping copies of the most recently used instructions that would normally be in the RAM so that our registers can get them faster. And aside from that, on the left-hand side, we've got the input devices and the output devices. That is what a computer system is made of: input, output, processing, and storage. Input devices, things like mice, keyboards, cameras, heat sensors, stuff like that, send information into the processor. If the processor is sending information out, like a video signal for a screen or audio, we'd have it in the output. All of those things you need to be able to talk about when we're talking about hardware. My last-ish slide on hardware is about how memory changes as we get further away from the CPU. So the best form of memory is this register. The register is the fastest memory that the computer can access, but it's very, very expensive. It's volatile, meaning if the power goes off, it disappears. And it is very, very small because it's expensive, so we can't put much of it on there. To make up for that, we have the cache, which is a little slower, but it's cheaper, so we can have more of it. Going out from there, it's the RAM, which is much cheaper, so we can have lots of it, but it is volatile, which means if the power goes off, it loses its data. Going all the way out to the right-hand side, where we've got our hard drive or our SSD, which is non-volatile, which means that we will be able to save data on it and keep it there permanently. It is very, very cheap compared to RAM, compared to any of the rest of it. It's bigger in capacity, and that's a key word there. It's bigger, not that it's bigger, it's bigger in capacity, but it is slow memory. You wouldn't want to be loading things from your hard drive. The last thing is the sizes. They could ask you to put these things in order or give you a selection of them. We start with bits, which is a 1 or a 0. 4 of those is a nibble. 8 bits is a byte. And that's where nibble comes from, because a nibble is a small byte. You see, comedy gold in computer science we are. Anyway, after that point, they're going up in thousands. Now, they're really going up in 1024s because binary. But as far as you're concerned at GCSE, you can assume they're going up in thousands. So 1,000 bytes in a kilobyte, 1,000,000 bytes in a megabyte, or 1,000 kilobytes, 1,000,000,000 in a gigabyte, 1,000,000,000,000 in a terabyte, and so on. Now, petabyte is roughly where we're sitting with servers at the minute. Petabytes of data are absolutely huge. You probably have terabyte hard drives at home, or you may have bought your new fancy PS5 in a terabyte model to make sure you've got plenty of storage. Petabyte is 1,000 of those. Exabyte is 1,000 of those. Zettabyte's 1,000 of those, and yottabyte is 1,000 of those. They think that all of human history, all of human conversation, everything can be stored in a yottabyte. And there's hardware. Now, it's a very quick summary of hardware, but that's hardware. The next one, though, is one you need to go off and practice, because this is your logical operations. And just to remind you, the gates you need to know about: a NOT gate, which is where we have the symbol with a line over it. If we put a value in, and the values that can go in are 1 and 0, we get the opposite out. So if a 0 goes in, a 1 comes out. If a 1 goes in, a 0 comes out. Worth remembering that, NOT gate. An AND gate has 2 inputs, A and B. It only gives us a 1 out the other side if they are both on as we go into it. So if A and B are on, they're 1s, we'll get a 1 out. Otherwise, it's 0. Now, this is the one where it starts to get a bit weird, because that is a dot. An AND is a dot. And it's weird because the OR, you'll remember, is a plus, which is quite difficult to parse in your head, because you normally say AND for that in your head, and it gets confusing. So the plus is OR. An OR gate either of those should be on. And that includes both of them. So basically, if either A or B is turned on or both of them are turned on, we're going to get a 1 out the other side, which is brilliant. But the really cool one, the Xor Gate, the X standing for exclusive. And again, the reason we use Xor Gate and not Eor Gate is because an Eor Gate is what keeps donkeys in a field, right? We're cooler than that. We've got the Xor Gate. The Xor Gate is an OR gate, but it only turns on if only one of them is on. So have a look at the truth table down there. When they're both off, it's off. When they're both on, it's off. But if only one of them is on, you can. Quick question, do we need to know the sign for the Xor Gate? Yes, you do. Although it's most likely they will write it in full if they use it like it is on the top there. But it's just the OR symbol with a little circle around it. So I'm sure you'll be fine with that. Okay. Here's an example question of a truth table. And I've nicked this from A level. So if you can do this, you can do anything. And it's reasonably straightforward. And I'll run through it really quickly. You'd get a question like this. And the idea, yours will be smaller, but I just wanted to show you this to show you how straightforward it is. Diagrams, you don't need to know the diagrams. I don't think for any of those gates. It's always the logic symbols as far as I've seen. I say that now, knowing our luck, we'll get the symbols in the exam. But they are all very straightforward. They're all in this presentation. We'll talk about simplification in a minute, but I just want to go through this truth table. So the first one is this, A or C. We're looking at column A and we're looking at column C. And if either of them have a 1 in it, we'll put a 1 in here. So no, no, yes, 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 yes. Okay, so we've done a column. The next one is B and C. So we're talking about this one and this one. Both of them need to be a 1 to get a 1 out of it because it's an and. So no, 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 yes, no, yes. Now this is where it starts to look a bit crazy, but actually A or C is this column. B and C is this column. And we're just XORing it. So we're XORing these two columns here. XOR, if they're different, we get a 1. If they're the same, we get a 0. So same, same, different, 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 same, different, same. Finally, this one, that entire expression there is this column. Not lets us have the opposite. So it's literally giving the opposite to this column. 1, 1, 0, 0, 0, 1, 0, 1. Okay, there we go. So that is a truth table. That is reasonably easy to do. Yours will be significantly shorter than that and probably worth about 4 marks. Make sure you know what you're doing. I'm getting on to graphics and stuff in a minute. This question, I'm going to jump to my top-down camera for that one because I move myself over here. This is about simplifying Boolean expressions, and you need to know the laws for this. I'll pop up the cheat sheet in a minute, which you can print screen if you want, but it is reasonably straightforward. If you get something like this, what you need to do is start applying the laws. Now, I can't see anything obvious that would simplify down here, so I'm going to multiply out the brackets. Treat it like expanding the brackets in maths. So to expand this side, I'm doing Q and Q, or Q and P, or P and Q, or P and P. Now, there are some laws that I can see there straight away, but what you've got to remember is that the and, the dot, is glue, essentially. That means that each of those are their own little separate entity, so you have to treat them separately. So first of all, if we've got repetition with an and, we can just put the single symbol. So that's true for the P as well. Now, Q and P, or P and Q, within that little box, we can swap the symbols around. So actually what we've got is Q or P, or Q or P. We can swap those symbols around. Again, in these chunks now, we've got repetition. The repetition means that we can remove a copy of them. So we're back to Q, or Q and P, or P. And we're mostly there. This would be a 4 marker. That is more or less there, but there is one more step. What I'm going to do is try and take Q out of this side. So I'm going to factorize out Q. Again, this is just maths. This is really just that same sort of maths that you've done before. We're going to pull out the Q, or the Q and, from this part. So Q out of Q gives us 1, just like you get in maths. So you take the term out, it gives you a 1. Q out of Q and P gives us P. And of course, this bit has to come down at the end. Now, this is gold. The moment we've got something in a bracket that's a number, a 1 or a 0, that means something nice is going to happen to this. Now, this is an OR where one side of it is always 1, which means that that entire bracket is just 1. Now, an AND with a 1 is just the term. So that entire thing boils down to Q or P. Now, I'm going to pop on the screen for you, just for you to print screen, and please do take the time to do this, a cheat sheet. Print screen that, and make sure you've got that for your notes today. That is the sort of thing you should be running through your head before you go into the exam. In particular, these here, the AND and the OR rules, are the things that simplify down the expressions. So they're the things you should be running through in your head. If you think about what that means as a circuit, you should be able to work it out yourself. For instance, A and 1 means that it's an AND gate. One of the sides is always on, so that means that that side doesn't matter. So it's just A. And if you can remember these 8 rules there, and again, you need to remember them forever, remember them long enough to scribble them down on the outside of the exam paper when the time starts, that's fine. Scribble them down, get them in there, and you're good to go. The rest of the laws around the side, to be honest, are just applying it. They're the factorization rules, really. So you can pretty much ignore them for most of it. It's those ones in the middle, the ands and the ors, that are worth remembering because they do allow you to simplify down things. Okay. We've done two parts of it in most of the time. So I'm going to try and speed up a little bit because networks, protocols you need to know about, all of that on there. TCP/IP, the transmission control protocol, and the internet protocol. That's the bit that lets you connect to a different computer. HTTP, the hypertext transfer protocol, transfers web pages and their resources, images, video, sounds, across the internet. HTTPS is the same thing, and it is secure, which means that we get encryption as part of that. FTP, file transfer protocol, is the transferring of files. The difference between HTTP and FTP, by the way, is that FTP just fires the data at you and doesn't check to see if it got there in any good piece, whereas FTP sends the information across and double checks that you've got every single thing. POP, the post office protocol, is what we use to receive email, but that's an old-fashioned one. If you take the email off the server, you can't see it anywhere else. So if you picked it up on your phone, you wouldn't be able to get that email then from a computer. IMAP, the internet mail, I've forgotten what that one is, but access protocol. I think it's internet mail access protocol. You might want to double check that. But what it does is it's the more modern version of POP. It keeps all your email on the server, and when you go and look at the things there, you can see the same view from everything, from your phone, from your computer, from your tablet, because everything is still there in the same place. SMTP, the simple mail transfer protocol, is the bit that sends the email. That's all it does. It sends the email to a server, not to the person, to the server. That's the bit after the @ and the server deals with it from there. Okay. Networks. Key to networks is that they let you share data, they let you share peripherals, things like printers, and connections to other networks. In other words, they let you share your internet connection, which is exactly the point of them. That's why they're so good. There are two key types of network you need to know about: a local area network, which has a small geographic area. In other words, it's usually over a building or a couple of buildings, or a wide area network, which is over a big area like countries or the entire earth, because the internet is the exact version of a wide area network that we want to talk about. Okay. Types of network. Ring network. This is how you label a diagram for it. Okay. Bunch of circles, they're the computers or the nodes. You label them, one of them workstations, you'd label one of them with server. You need to make sure you've got the arrows going in the same direction. This is because in a ring network, the data only flows in one way. What happens if we take one of those nodes off? Well, if we unplug one of these computers, everything goes off because the data is trying to flow around in a circle. But the data can't collide with the data. Exactly. One cable breaks, the entire thing goes down in a ring network. It is only really good if you've got a couple of computers. It is very, very cheap, very, very easy to set up. You probably wouldn't want to build this properly. Bus network. This is a great one for rolling out temporarily, because what you've got is this bus cable across here. A bus cable is a really chunky, really powerful, high bandwidth cable, and you make everybody plug into that. So this would be good for like rolling out in a, imagine you've got like a video games competition or something. You've got everyone bringing their laptops and they want to plug into Ethernet. You'd roll out this bus cable, everyone would plug in, you'd have a really good connection. If any one computer goes off the network keeps going. On the edges, you've got these two things called terminators. And what they do is if data gets to one side of them, they send them back the other direction. So data's going both ways on this cable. So you do have the opportunity for data to have a collision and to corrupt on that bus cable. Now, the point of having two terminators is if you send a message from this computer and it goes to the left and it's sent back all the way to the right and it's sent back all the way to the left again, well, the computer it's looking for isn't there. So if it's not there, the terminator destroys that data, so it's not just pinging back and forth forever. This is the exact diagram you need to draw for bus. And if you're asked about what network is great for temporarily rolling out, this is the best one. Star network's the best network for like most situations. You have your server and your workstation and everything's plugged into a switch. A switch is a clever device that routes traffic. So if a message is going from my workstation to my server, it goes to the switch and then straight to the server. If I'm sending a message from the server to the top right one, it goes from the server to the switch, and straight up to the right. All of that network system is designed to be nice and efficient and to route traffic around it. No part of that network is going to cause problems to happen unless we disconnect the server, which is always going to cause a problem. That's the most robust, but it's expensive. Switches of that level, really, really, really expensive. So Star Network, the best. I can disconnect anything apart from the server and it'll keep working. I can add more in very, very easily, but expensive. Okay. I made this diagram, didn't really realize it looked like a pentagram until just now, so apologies, but this is a mesh network. In a mesh network, every computer connects to every other network on that diagram. So there are multiple ways for us to get the information from one computer to another. It's the best type of network because there's multiple ways of us connecting. Every computer is directly connected to another. But that's not the way most networks work. This would be the most expensive thing in the world if we did this in school, because every computer would need, if there are what, something like 400 computers just in the downstairs part of our school. Every computer then would need 399 cables coming out of it into everything else. This is more what we have in the real world. This is a partial mesh network. So the computers are all connected together, but indirectly. If I want to get a message from this computer to this computer, it has to pass through this one, and get back up here. And that seems familiar because that's the internet. The internet is a partial mesh network where Every computer is connected together, but you might have to send it through 4 other computers to get to it. And those computers might be all over the world. So that's what you get. Our layers. Lots of people hate layers. It's not that bad. If you think about the top end as being the program sending the message, and the bottom side as being the raw data that's going to come out of it, like physically ones and zeros as electrical pulses or radio waves, then that's the best thing to remember. You may have to remember the names of them, so it's worth going over. Again, this is one of those things that I would have printed out as I'm walking into the exam, and I'd be going over it and over it and over it. Stick it in your bag, go over it and over and over and over it. And the moment the exam starts, I'd be jotting it down in a blank piece of paper as quick as I could, get it out of my head onto something useful, because it's hard to remember. So if an email application wants to send an email, it talks to the application layer. The application layer goes, cool, this is an email. I'm going to send it via SMTP. Pass it down to the transport layer. The transport layer is the bit that breaks it into packets. It goes push, 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 push. Here we go. Passes it down. The network layer is the bit that goes, right, where are these packets going? Let's find the best direction. Let's find the correction for them. Cool. The data link layer then, that's job is finding the best possible path and combining them together into a sort of a group that it can send. And finally, the physical layer is the bit that actually does the turning it into ones and zeros. It turns it into the raw data and sends it. So across the internet then, this raw data travels and it arrives at your computer, and your computer gets it at the physical layer, converts it back up into a chunk of data. The data link layer breaks that up back into the packets and the protocols and stuff and sends it back up to the network layer. Network layer checks those packets, puts them back together. Transport layer goes, whoosh, it's a file again. Back up to application layer. Application layer goes, oh, this is an email. Here you go, email program, have it. So all of that stuff is important. Now, you do have this, those of you in my class, you do have this in your Google Classroom. Go to the communications one, go to the layers part, and reread through what each of them does, because I've simplified it a lot here just to make it simple in the time we've got. It's not simple. You need to go practice that one. Please do, just in case. Right, lots to do, 20 minutes to do it in. Organization and structure of data. We're going to bomb through this. You need to know your conversions. Binary to Daenery. Daenery is our number system. Binary is this. You might see it written down as a number with a little 2 on it. That means binary. A number with a little 16 is hex. And a number with a little 10 is this, our Daenery number system. The one we use because we have 10 fingers and thumbs. So we are used to counting in tens. How do we convert from binary to Daenery? Well, it's very, very easy. We put our place values up. Remember, the place values always go from right to left. We start with 1 and we double it as we go. So that's an 8-bit byte there. And the ones basically mean where we've got a 1, those place values are added up. So we just add up those place values where there's a 1, and you get your Daenery number all together. There's a good example for you there. Again, my lot on Google Classroom, you've got all the workbooks and all the QR codes to scan to see that if you want to practice it as much as you want. Okay, doing it the other way around, turning from Daenery to binary. Draw out your table with your place values and go from left to right. And every time you're moving, you're saying, can I take that away from the number I've got on the left-hand side? I can't take 128 away, but I can take 164. So I can take 64 away. If I take 64 away, that means I've used it. So take 64 away from the number, and that's what we're working with. Can I take 32 away from 29? I can't. Can I take 16 away? I can. So let's use 16. 13 left. Can I take 8 away from 13? I can. I've got 5 left. Take 4 away from 5? I can. I've got 1 left. Can I take 2 away from 1? Nope. Can I take 1 away? I can. You'll know it's right because you'll end up with a 0. Boom. There's your binary. Binary addition, reasonably straightforward. Those numbers on the top are what I'd write down. You need to write down the binary version of 0, 1, 2, and 3. So 0 is 0, 1 is 1, 2 is 1, 0, and 3 is 1, 1. And then what we do is we work through the sum from right to left, and we do it just normal. So 1 plus 1 is 2. Now, 2 can't be written in binary. It's 1, 0. So we bring down the 0 and carry the 1. In the next column then, I've got 0, 0, 1, which is 1. Final column, 1 plus 0 is 1. Simple as that. You have 8 of them to do, though. Thing to remember about binary addition, though, is we can get to a situation where we've got this thing, the overflow. So what's happened here is that the sum needs an extra bit. It's gone over the 8 bits that we need to hold it in. And if that's the case, we can't actually store that. This isn't normal maths. This is a computer. Those 8 bits are a physical circuit that we've got to deal with. So at this point, that 1 is actually lost. It's overflowed, and we can't see it. Quick question was, are we allowed calculators in the exam? You are, so please bring them with you. You are allowed calculators. Please do bring them with you. I will have some ready to go in case you've forgotten them, but they'll be Miss Viner's, and she will break my legs if I lose them. So I'll need them back if you're borrowing mine. Okay, and they are very low-tech calculators. Best bring your own fancy scientific one. Okay, you could have binary subtraction. Works just like normal subtraction, except we need 0, 1, 2, and 3 at the top to remember it. So if I do 1 take away 1, that gives us 0. Now 0 take away 1, I can't do, so I'll have to borrow from the left-hand side. If I borrow from that, I end up with 0. And what I'm left with on my side is 1, 0, which is 2. 2 take away 1 is 1. And on the end, 0 take away 0 is 0. Boom, you're done. I've never seen a question of binary subtraction. I'd be surprised if it popped in there, but it is in your spec, so it could technically happen. Okay, hexadecimal. Key thing about hexadecimal is it uses base 16. There are 16 values in any one place. That means when we get past 9, we need to use letters to represent them. We use A to represent 10, and we go to F. As long as you remember A is 10 and F is the last letter, you can just write this out in your margin and work it out for yourself. A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. In this example, what we're saying is we have E lots of 16 and 1 lot of 9 because the place values are different in a base 16 number system. In binary, they doubled because it was base 2. In this one, every time we move to the left, it times it by 16, which is why you only need to know 2. So E16s is actually 14 16s. 14 16s, which you all know off the top of your head, surely, is 224. 224 plus 9 gives us 233. Nice and straightforward, hopefully. Other way around, this is the most difficult method, but it's reasonably straightforward if you can get your head around it. What we need to do is find out how many 16s are in this number. So 213 divided by 16, that gives us 13.375. Don't care about the decimal. I want the whole number in that box. 13 doesn't fit, so that means I need to put the letter version. The letter version of 13 is D. So what I've said is I've used 13 16s. Well, let's see what I've used. 13 16s is 208. So 213 minus 208 is 5. That number goes in the right-hand box. Boom, done. Simple. That is the most straightforward way you can do it. Do the dividing by 16, the whole number goes in the left. Work out how many of you you've used. Whatever's left goes in the right-hand side. Smashing. Binary to hex is where the magic happens, because the reason we need to know both is because 1 hex bit is 4 binary bits. So 1 hex bit is a nibble. So to convert them, you do this. Split them in 2. Instead of treating it like one big thing, you split it into 2, right? And what you do with that is you work out what each of them are in Daenery. So 1011 is 11, 0010 is 2. You're going to write the number 11 on the left-hand side, the number 2 on the right-hand side. Of course, 11 doesn't fit, so 11 is B, B2. Other way around is just as easy. Split them. Work out what they are in Daenery. A is 10, F is 15. Represent them as 2 4-bit nibbles. 1010. On the right-hand side, 1111. Then you just go push them back together. That's it. You're done. I'm going to pick up on something from the chat, see, because a few people are asking about calculators. WJEC is allowing calculators. I don't think Educast and the English boards do. Certainly, that's not my memory from when I was teaching in England. But WJEC, definitely, calculators are good. Okay, bitwise or shifting. If they ask you to shift to the left, you're basically moving it to the left 3 places. 1, 2, 3. Notice we've overflowed. We've lost some of that data. It's gone out of the boxes. What do we put in the blank ones? Zeros. That simple. If it says shift to the left, cross out the left numbers to that amount and add zeros on the opposite side to the same amount. Shift to the right. We're going to move it to the right 5. 1, 2, 3, 4, 5. And fill the blanks with zeros. Again, I'd be crossing off the 5 numbers on the right-hand side and adding 5 zeros on the left. Simple, easy, straightforward. Text. Text is represented by every letter, every symbol having a unique binary value. In Unicode, that's a 32-bit byte, so 4.2 billion possible numbers. That means we can include emojis. The pile of poo emoji is actually the number 128,169. So when a computer sees that, it goes and loads that image into memory and goes, bloop, there we go. Images are stored in things called bitmaps. They're a bit more complicated. It's basically a grid, and for every bit, we store the color value. This is a black and white one, so it's going to be ones and zeros. But if we store the color value of each pixel, that will mean that we get a little bit more flexibility in what we can show. And of course, we can show full color images. But each pixel wouldn't be 1 bit then. It's probably going to be at least 32 bits to store the red, green, blue, and the light and the darkness of each pixel to get that data in. Sounds, of course, are waves in the real world. So what we need to do is represent that wave. We take samples of it or recordings of the amplitude, that's just the volume, many times per second. The more times we take it, the higher the sample rate, the better we can represent that. Here's an example of a wave on the left and the recreation on the right. Now, clearly, that's going to sound terrible. Look how blocky it is. The more samples we take, the better the quality of audio. And just so you know, the level of samples that you need to take to make music is 44,000 per second. Each sample is stored as a 32-bit value, which means that we need a significant amount of data and a significant amount of bit depth to store audio properly. Data types. You know this from programming, but we've got our numbers, integers and real numbers. Integers are whole numbers. Real numbers have a decimal part. We've got characters, which are letters, strings, which are collections of characters, Boolean, which is true or false, and date and time. Now, date and time, although that's a data type, you wouldn't really use it in programming. It's more for databases. Arrays are lists, and we've got 2 types. We've got our 1D array on the left. So if I wanted to access maths, I'd access it by saying the name of the array, square brackets, and the row number. Notice we start from 0 because they're indexes. A 2D array, I would always do the row first and then the column. So in this case, it's different from geography. It's different from maths. We do the row first and then the column. So this would be row 2, column 1 to get Mrs. James. It's the row and the column for a 2D array. But a 2D array is basically that exact thing. It is the table. Types of validation and verification. There's a big bunch there, but the ones we've done, the ones you remember, hopefully. Presence check, is it there? Length check, how many letters, how many characters? Range check, is it between 2 numbers? Lookup, is it part of a list? Format, does it look a certain way? Type, is it an int? Is it a float? And then we got verification, which checks something is correct. It has been added correctly. And that would be dual entry. We would type it in twice like a password, and proofreading. The chat looks like it's gone a little bit quiet. So if somebody could say something to me in the chat, just so I know it's working, that would be amazing. Okay, 3 to go in 12 minutes. This is a bit of a tight one. Programming construction. This is a weird one. Good. Thank you, chat. I know you're still there. So on the right-hand side of this screen, okay, we've got our low-level code. It's our ones and zeros that are being run by the processor. This is machine code. To update a screen with 1 million pixels, which isn't a lot, to update a screen with 1 million pixels, we have to have about 8 million instructions in machine code because we need to load the color value of each pixel and push it to the screen. That's a lot of machine code. Machine code is hard to read for a human. So we have a version of that called assembly code, which is where instead of 1101 as the instruction, we have a mnemonic, a word to represent it. Things like add to represent addition, dat to represent data, and imp to represent input instead of binary numbers. It's easier to read, but for every line of machine code, we need 1 line of assembly. So again, if we're putting images on an image that's 1 million pixels in size, we need 1 million lines of assembly code. We call that low-level code because It's close to the CPU. Now, we don't write in that. We write in high-level code, something like Python, where each line of code could be 2 million lines of machine code. So the question is, why do we write in high-level code, and what does it do? Well, high-level code is just easier for humans to read. It's more like human language. Now, the types of programs we need to make that work, there are two types. The assembler over here is what turns assembly code into machine code. And it's a reasonably dumb program. It's taking each of these and just translating them into the binary. Our interpreters and our compilers turn high-level code into machine code. So again, for each line of this, they could be outputting possibly 2 million lines of machine code. So that's a bit cleverer. And there are two types. There's an interpreter, which does it live. It does it line by line as you go. Or there's a compiler, which does it in advance. Think about it this way. It's the difference between having somebody with you as you walk around Paris, translating everything somebody says into French and English for you. And a compiler is somebody that's gone and translated a book for you in advance and just hands it to you. The difference is really, really subtle, really. An interpreter, you can run it anywhere as long as we've got the code. With a compiler, you need to compile it for every type of CPU. So you need to compile for each games console, the PC, the Mac, different phones, which is a massive absolute faff. But what you do get is just machine code. So compiled code runs really, really, really fast. Interpreted code runs quite, well, not quite slow, but slower. So if you're building a video game, you want compiled code. Compilation takes this process. I'm not 100% sure this will be in the exam, but it is part of compilation, so I thought I'd bring it up. We take our code and we do lexical analysis, which is where we take all the words and we separate them into what we call tokens. So basically, each word is a separate thing. We then look at our keywords like for and if and stuff like that and mark those up. And we get our identifiers, our variable names, and we store those. We also get rid of the white space, the tabs, the spaces, all that sort of stuff. So we're left with a bunch of tokens, list of keywords, list of identifiers, and we pass it on to the syntax analysis. Syntax basically says, are these in the right order? Have you got keyword, bracket, variable? If so, cool, we'll pass it on. If not, we're going to error and stop. Semantic analysis, semantic meaning, good little joke there, but it tries to understand what you were writing and it goes, does this make sense? Are you trying to glue together a letter and a number, or are you trying to add 7 to a video? Does it make sense? And if it doesn't make sense, it's going to error and it's going to pass it on. Now, code optimization happens at this stage. When we generate the code, we're generating ones and zeros. So this is the bit that takes that one line of high-level code and turns it into a million lines of code generation. At this point, it tries to make it a bit more efficient and tries to put in a few little cheats to make that run better. So instead of outputting 3 million lines, it might only output 100,000 to make it a bit quicker, but using some clever tricks. Okay, 2 more. 7 minutes. This is going to be tough. Security and data management. There's a mass of this. Am I definitely muted? What's happening here? Let me have a look. Please let me know if my audio is still working. It seems to be transmitting, so I'm going to keep going. Good, thank you. Right, security and data management. I'm bombing through this very quickly. So, data security. Dangers you need to be wary of. Hackers, malicious and accidental damage. Now, what's the difference? Malicious is I'm damaging something on purpose to cause problems for you. Accidental is I work for you. Whoops, I've pressed delete and deleted all the orders or all the grades. Ransomware. I install a piece of software, it locks my computer and maybe encrypts my data until I pay them in Bitcoin to have it back. Loss of anonymity as well on the internet. You might be able to find out who I am from my online presence. Now, disaster planning is something they might ask you about. There are 3 stages to disaster planning, and this happens with everything. It's not just like what happens if somebody hacks us. It's also what happens if the server gets flooded or it breaks or it's on fire. We need to plan what's going to happen before, during, and after. So beforehand, we'll think about all the things and we'll put a plan in place. When it's actually happening, we'll look at that plan and we'll use it. So who do we call? What do we do? What are the steps to notify people or to protect our data? Afterwards, we have a plan of action to get everything up and running again. and get it all back to the way it was. But also we do our little evaluation then, and we see what can we do better. How can we make that better long term? So next time it happens, it'll work perfectly. Data management is about backing up your files. Key thing of backups is you keep a copy. That's the key word. A backup is a copy of some files in case it deletes or you remove it and you need to come back to it again. Backups tend to be generational, and you remember this was grandfather, father, son. The idea behind that is we always have 3 backups, and whichever is the oldest, we delete that and we put the newest one over that. So the grandfather becomes the son. So we've always got 3 generations of backups, the youngest, the middling one, and the oldest. And we always take the oldest one, delete it, and put the new one on it. So we've always got the 3 most recent backups. Archiving files, that's different from backing up. That's moving data from your computer somewhere else, and it's data that you're not using much anymore. Good examples of this might be, we'll take the students that have left this summer and put them on an archive disk. We've still got that data, but it's not clogging up the computer I'm currently using. You've got a better example, I'm sure. You've downloaded videos off the internet, certainly legally, and you probably don't want them clogging up your hard drive. So possibly what you've done is you've moved them to like a USB drive or something like that. Okay, network security then. So what network security is how we are dealing with, sorry, 1 second. There we go. Okay, it's how we are dealing with our network and making sure it's protected, and that's limiting levels of access. So different users have different levels of access. I can save things, other people can edit things and stuff like that. Using strong passwords, making sure our password isn't just like our name or password or welcome to with a capital W. Using encryption, so making sure that our data is actually encrypted. And then we've got things like network policies, acceptable use policies. That's what you say yes to every time you sign into the computer. You will do good things with the computer. You won't bully anybody. Backing up on our network, making sure we've got backups. So if things get deleted, we can restore them. And our disaster recovery plan, that's where that comes into mind. Cybersecurity then, very, very quickly, you need risks and protections. Key things to think about: viruses, software that will damage your computer. I've said works there, but I meant worms, I'm sorry. Worms are self-replicating things on a computer. They're not necessarily malicious, but they will take resources. Spyware, spies on you. Keyloggers, the worst kind of spyware, literally send your key presses up to the internet somewhere. And Trojans are a way of getting viruses and all these things that look like it's a nice piece of software or something good. If you've downloaded Adobe Photoshop cracked.exe and you double click on it and nothing happens, probably a Trojan. The protections then, well, you need antivirus software, and that needs to be up to date. You need an antivirus software works by identifying what looks like a virus and getting rid of it. You've also got firewalls to stop people connecting to your computer. You'd update your OS and update your browser so you're not working with an operating system or a browser with security problems. And you're going to avoid phishing emails. If you get an email from a Nigerian prince, probably best not to answer it unless you know that Nigerian prince very well. Right, 2 minutes. Cyber attacks, different kinds of attacks. SQL injection attacks, where I type something into your website that looks like code and it takes over your website. DDoS, you find an IP address and you get millions of computers to connect to it, causing the server to reboot, and you keep doing it. Password attacks, trying to guess people's passwords, but more complicated with programmatic ways. IP spoofing, pretending to be somebody else on a network. Social engineering, the best one. Calling somebody up, pretending to be a person and asking for their password to be changed. How do we find these vulnerabilities? Well, footprinting, where we work out what a company is doing and we understand what data it shares, and we can get an idea about the footprint of the company and where it extends into the real world. Ethical hacking, where we get some good guy hackers to go and break into our systems and tell us what's wrong with it. And then penetration testing, where we get those same hackers to try and break into our network with our permission internally. We'd also want to be designing for security when we're building our network. So we're always constantly testing with these methods, and we're always trying to use best practices. Nearly done. One more. So the only ethical and moral topic you've got to talk about, and which is probably going to be your essay question at the end. And just a reminder, all of these questions you can answer with bullet point full sentences, but the last question, the essay question, must be written, if it was bullet point sentences, as if it was an essay, and it must flow. It must read sensibly and make points. It can't just be, here are 15 things that I remembered about it. They need to be structured in a way that you're making an argument and it's progressing. So, key things to think about. Are computers recyclable? Some of them are, some of them aren't. They should be recyclable. Apple computers are more recyclable than others, but then you have to pay more for them. If you are going to use computers, like in our school we use iPads, does that mean we don't use as much paper? Well, it probably does. But does that offset the electricity use? And if we're generating electricity with fossil fuels, is that better? We get deliveries for everything now with Amazon and other companies. Is that good for the environment? Computer rooms need air conditioning. Is that good for the environment? Here's a good one though, remote working. Your parents or you working from home means you don't have to drive to work. You're not all in the city centre. There's less transport infrastructure. There's less people, smaller offices, smaller electricity use. All that sort of stuff would be good without having to travel. And we're done. Good luck for tomorrow, everyone. Go and do some revision now. I'll get these slides on as quick as I can. I've got just about 5 minutes till year 12 come on and start bothering me for things. If you've got any questions, please, we've got about 30 seconds, so stick them in the chat now. And I'm going to have to go then onto my other live stream for year 12, who'll be waiting with anticipation for me. Oh, thank you guys. I really appreciate it. Thank you all for tuning in. There's many more of us watching than are actually in my class. So all of you that popped along for a bit of extra revision, thanks very much. But those of you in my class, make sure you smash this exam tomorrow. I do believe in you. You're all brilliant people. You can do this. And more than that, you can do it with style. We can really get something cool going on. The VOD will be available on Twitch straight away after. I'm going to turn the live stream off now because I do have to go to the year 13s. Thank you, everyone, and I shall see you.